Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to give an overview of the topics related to multiple continuous variables. The goal is to give you an overall picture of how these topics fit together. So don't worry if you don't understand some of the details, they will be provided in the individual videos on each topic. Let's get to it. We're going to talk about multiple continuous variables. We will start by explaining the mathematical framework that enables us to model multiple continuous quantities together. Then we will talk about the joint probability density, which is the user interface, if you want, of these models that have multiple uncertain continuous quantities. Then we will talk about marginal and conditional distributions, which enable us to isolate the behavior of individual variables within a model and also to update our uncertainty of certain variables once the value of other variables is revealed. And finally, we'll talk about Gaussian random vectors, which are the most popular parametric model for multiple continuous variables. All right, so how do we represent uncertain continuous quantities? We represent them as continuous random variables. How do we describe those random variables? We describe them in terms of the probability that they belong to any interval within the real line. What do we do when we have multiple continuous quantities? We represent them as multiple continuous random variables within the same probability space. In a moment, we're going to see that that is crucial. How do we describe those multiple continuous quantities in terms of the probabilities that they belong to certain intervals at the same time? Let's see what I mean. Here we have two random variables, A and B. So A, we're going to imagine, is related to this real line that I drew here, to the horizontal axis. And B, tells us what point we are on the vertical axis. And now we can imagine a 2D vector, AB. And we can ask ourselves, how can we describe this 2D random vector probabilistically? Well, a very reasonable way to describe this 2D random vector probabilistically is in terms of the probability that it belongs to different rectangles. Why rectangles? Because a rectangle in this 2D plane essentially tells us when this random variable belongs to a certain interval, in this case this interval, and this random variable, the other random variable, belongs to some other interval at the same time. Okay, if these random variables are in these intervals at the same time, then the random vector is in this rectangle. And of course, we're going to talk about rectangles because it's kind of easy to visualize, but what we're going to say will hold for any union of rectangles, which allows you to essentially build any reasonable set in 2D. We call such sets that can be built as a union or even a countable union, a union of countably infinite rectangles. We call these Borel sets, okay? And that actually encompasses almost any reasonable set that you would encounter when you're doing, definitely when you're doing data science, even if you're just doing math. Okay, I got a little bit sidetracked there. The point is, we're going to describe these 2D random vectors as in terms of the probability that they belong to this rectangle. So now we have to ask ourselves, is this probability well defined? Well, the probability that the random variable A is within this interval must be well defined if it's a valid continuous random variable. This here denotes the sample space of the probability space associated to the random variable. And remember that random variables mathematically are functions from a sample space to the real line. So you see here, this point here actually, maybe I should draw this point here is mapped by the random variable here. And this square that is gray contains all the outcomes that map to that interval through the random variable. So the random variable maps the outcomes in that event to that interval. So now if you remember, in our definition of continuous random variables, we impose that the probability that the random variable ends up in any interval is well defined, which means that the event, this event that contains all the outcomes that map to that interval must be assigned a probability by the probability measure of the probability space. It must belong to the collection of events that are assigned a probability in the probability space. Okay, so that event is well defined. The same holds for the event that the random variable b is in that interval. Here, you need to, I'm not sure I said this explicitly, but I will say it now, a and b are defined on the same probability space. So this guy and this guy is the same. Of course, these events are going to be very different because these are two different random variables, but they're defined on the same probability space. If the random variable b is a valid random variable, then all of these outcomes that map to this interval, okay, they form an event that has an assigned probability. It belongs to the collection. The probability measure has to assign it a probability by definition of a valid continuous random variable. So now we can go back to ask ourselves, what is this event that we're interested in? The event that the 2D random vector ends up on this rectangle. Well, it's just what has to happen for that event to occur. A has to be in this interval, B has to be in this interval. So that event is the intersection of this square and this circle. And by the properties of probability spaces, the intersection of two events that are assigned a probability must be assigned a probability by the probability measure, so that event is well defined. In general, once we have continuous random variables that are defined on the same probability space, automatically the probability that they belong to intervals at the same time, or equivalently, that random vectors obtained by stacking these random variables as entries, the probability that those random vectors are in rectangles in the case of 2D, or hyperrectangles in the case of D dimensions, is going to be automatically well defined. The summary of all of this is basically that because of this framework where we're defining random variables as functions within the same probability space, the probabilities that we are interested in, which is that the random variables belong to intervals at the same time, are always well defined. We don't have to worry about anything. It works out mathematically. Of course, as usual, we're going to forget about all of this business, and we're just going to manipulate the random variables with an object that is the joint PDF. But it's, I would argue that it's good for you to know how this mathematical framework works, even if you're probably not going to touch it very much when you're doing data science. Anyways, so just mathematically, very briefly, what are we saying? If we stack random variables as random vectors and we consider the probability that they belong to this Cartesian product of intervals or of unions of intervals, these guys can be intervals or unions of intervals, then the corresponding probability is going to be well defined. Just to be clear, this Cartesian product corresponds to the rectangle that we were talking about. Okay, so what is the set of events that map to the rectangle? Well, it's a set of events for which the outcomes map to one of the intervals through A and to the other interval through B. It's the intersection of the pre-image of those intervals through A and through B. We've seen that that intersection must be assigned a probability. Things are fine. The same can be said, and I won't go into a lot of detail because it's the same idea, when you have D random variables instead of just two. The key ideas here is that we're defining them on the same probability space. So then when we consider this Cartesian product of intervals or unions of intervals, we're going to have these hyperrectangles in D dimensions. The probability that the random vector obtained by stacking the random variables belongs to those hyperrectangles is going to be well defined. Everything is fine. Okay, perfect. Everything is fine, but of course we never do this explicitly, all right? We need this mathematical framework in order to be able to formally define the random variables so that we can capture their interactions mathematically, but then we add like another layer. And by another layer, I mean we add some tools that enable us to encode the probability that we're actually interested in without explicitly defining the underlying probability space. So remember that in the case of discrete random variables, These tools were like the PMF and then the joint PMF when we had several random variables. In the case of continuous random variables, they're the CDF, the cumulative distribution function, and the probability density function in the case of a single random variable. Now, for multiple continuous random variables, we're going to define generalizations of those two objects. So remember that the CDF is the probability that a random variable is smaller or equal to any value on the real line. The joint CDF is the probability that, well, for two random variables, the joint CDF is the probability that they're smaller or equal to any pair of values that are on the real line. Okay. For D dimensions, basically here each entry is more equal to than is smaller than or equal to certain values that are the entries of that deterministic vector. So the joint CDF is important because it allows us to essentially completely characterize the behavior of the random variables, but it's very annoying to manipulate. For example, imagine that I want the probability that these two random variables are within a rectangle, okay, if you stack them as a 2D random vector. This rectangle is basically like this. Okay, it's this rectangle here. And that's not a rectangle. Let me try again. That's a rectangle. Okay, so the probability that the two random variables are within that rectangle can be expressed in terms of the joint CDF, but it gets pretty complicated. Okay, so before I show you, let me tell you, it's the CDF here. Sorry, it's the CDF here minus the CDF here and here plus the CDF here. Okay, that's the formula. So as you can see, and this is for a simple rectangle, when things get a little bit complicated, using the joint CDF to actually represent probabilities in practice gets very annoying. So we actually don't do that usually. Instead, we use the probability density of the random variables or of random vectors equivalently. So what is the probability density in multiple dimensions? Remember that in one dimension, the probability density is essentially probability divided by the length of an interval when those intervals go to zero. And that gives you a local measure of how much probability there is, what is the likelihood that the random variable actually lands at a certain point. And it's more useful than the CDF in the sense that it gives you local information. Here, we want a probability density over two random variables. So instead of the length of an interval, we're going to consider the area. So what we're saying here is that the probability that the random vector formed by the two variables is in a small square close to AB, or a small rectangle. In this case, it's a square because we're going to take the sides to be the same, is equal to the density multiplied by the area of the square as the area goes to zero. Okay, so it's the same idea, except that instead of length, now we have area. If we go to 3 dimensions, we're going to have the same with volume. In higher dimensions, hypervolume. I'm not even sure what is the generalization of volume to higher dimensions, but I hope you get the idea. We show this in the video on probability densities, but we can express the joint probability density as the partial derivative of the joint CDF with respect to its two coordinates. Similarly, when you have the coordinates, you'd have to take the partial derivatives with respect to every coordinate. This kind of makes sense because we're seeing the change in the probability in terms of all of the coordinates. And as we will see in a moment, when you integrate this thing with respect to all the coordinates, you get the probability that the random variable is there. Hopefully that makes sense. All right, so how do we use the joint PDF to compute probabilities? We just integrate over the relevant set. So the probability that these two random variables are within this 2D set can be obtained by just integrating the joint PDF over that set. Same thing for D-dimensional sets. We just integrate the PDF over that set. These are Borel sets which is just a fancy way of saying they're unions of rectangles in 2D or hyperrectangles in D dimensions. All right, so let's take a look at an example. This is a running example that we use for many of the topics related to multiple continuous variables. There's this otter that is swimming around in this lake, and we model the position of the otter, of this animal that is swimming around, as having constant density within the lake, which is that triangle, and being 0 outside. So the otter cannot be outside. What is the density? Well, the area of the rectangle is 1/2. Joint PDFs, I didn't say it, but they have to integrate to 1. So the density within the lake is equal to 2. How do we compute probabilities such as the probability that A is above 0.6 and B is below 0.2? Well, we have to integrate. And in this case, the integral is just going to be computing this area because the density is constant, and multiplying by the density, multiplying by 2. So that area multiplied by 2 is going to give us the probability. In this case, that probability is 0.12. This is what maybe I should have said a little bit earlier so that I could explain why the density was 2 in the lake example. PDFs have to be non-negative and integrate to 1. And once you have a function of 2 variables that is non-negative and integrates to 1, it's a valid joint PDF in the sense that we could construct the underlying probability space, even though we never do that. Same for D variables. If you have a function in D variables that is non-negative and integrates to 1, you have a valid joint PDF. And it is the joint PDF what we usually estimate from data. It's not, we never construct this probability space explicitly. Okay, it's good to know that it's there in case a mathematician corners you and questions what you're doing, but we never really build it explicitly. We just estimate the joint PDF directly from data, and then we know that there will be a valid probability space. So how do we estimate? So this is what the data looks like in this multidimensional setting. We have 2 continuous quantities, and the key thing to emphasize is that each data point has 2 coordinates. So we do need data points that give us the 2 quantities, examples of the 2 quantities of interest at the same time, because otherwise we cannot model the joint behavior of those 2 quantities. The same thing when we are considering D quantities. Okay, so once we have these data points that do tell us, provide examples of the 2 quantities at the same time, how do we model their density? Well, we can use a multidimensional generalization of kernel density estimation, where essentially we put a little mountain of density at each point. So the point is under here. We put a little mountain of density at each of the points, and then we add them together. And now if those little mountains have volume 1 underneath, and we divide by the number of points, when we add them all together, the whole volume, because these are non-negative functions, is going to integrate to 1. So the whole function is going to integrate to 1. It's going to be a valid density. And that's multidimensional kernel density estimation. It's important to emphasize that this is only going to work in low dimensions. When we have, 2 variables, 3 variables, 4 variables, as we increase, this is going to become increasingly intractable because of the curse of dimensionality. We talked about the curse of dimensionality in detail for discrete random variables. The problem when you have several variables is that at some point there's too many possibilities. The possibilities explode exponentially. You're never going to have enough data to compute the probabilities that you're interested in unless you enforce some dependence or independence assumptions. The same happens with continuous variables, only it's even worse because each of the variables can have infinite values on an interval. So it just gets worse. So this is very nice, but it's mostly going to be useful in low dimensions. All right, these are the contour lines of this object. The contour lines essentially tell us where the density is constant, okay, on these mountains. And it's usually a cleaner way of visualizing joint probability densities. Okay, so this is just a mathematical definition of multidimensional kernel density estimation. This K is the function that tells us how these mountains look like. Something important to point out, and realize that we're adding it over all of the data points, dividing by the number of data points so that it integrates to 1. Something to realize is that there's this parameter h, which is going to govern how spread out these mountains are. And depending on the amount of data, that is really going to affect our estimate of the joint density. Just to show you, this is a scatter plot of data points that tells us that the hourly temperature at Versailles, Kentucky, and Manhattan, Kansas. And realize that here we do have a situation where each data point is associated to the two quantities that we're interested in. For each data point, we know what was the temperature in Versailles, what was the temperature in Manhattan at the same time. All right, so now here we can apply multidimensional kernel density estimation. If we use mountains that are not very spread out, the bandwidth, this parameter is called the bandwidth, is very small, then we overfit, right? We don't really believe that this is, a true feature of the density. That just happens because there's an isolated data point. If we had more data points, there would be more data points around there. So if we increase the density, we can smooth out this noise, which is great. But if we pick a bandwidth, if we increase the density, if we increase the bandwidth, then we smooth out that kind of noise, which is great. If we increase the bandwidth too much, these mountains become too spread out. We can over smooth and lose some of the meaningful structure in the data. All right, so what if we have several variables within a model, but we only care about some of them? We don't care about the rest. How can we characterize the behavior of those variables using the joint PDF of all the variables in the model? In the case of the triangle lake, what if we only want to know the density in this direction? We don't care about what's going on in this direction. Well, what we can do is we can integrate the joint PDF with respect to the other variable in order to obtain the marginal, what is called the marginal PDF of A. That's just the PDF of A as a random variable. Because it's important to remember that these random variables are still random variables defined within a probability space. So it's legitimate to just define their own probability density without referring to the rest. Okay? Because sometimes we forget, right? When we're jointly modeling several random variables, these random variables can exist on their own. And in order to isolate their individual behavior, what we do is we integrate the joint PDF with respect to the remaining variables. In this case, this is what we obtain, which makes sense. And I think in the video on marginal distributions, I actually described this for B instead of for A. So here, clearly, there's more probability that A is there than there. So this is why the probability is higher here for smaller values than here when we look at the marginal PDF. I think in the video on marginal distributions, I did the other way around, which is fine because B clearly has the same marginal distribution here, right, by symmetry. But anyways, when you have more random variables, it's the same idea. Here, I'm showing you what the marginal of one entry of a d-dimensional vector looks like. And essentially what you do is you fix that value for that entry that you're interested in, where you're interested in finding the marginal density, and you integrate over all the rest. Okay, you integrate over all the rest. Here, we ran out of space. I didn't realize I should have fixed the slides. But anyways, you can see what's going on, right? All right, so here in our temperature example, if we do that, if we integrate the joint PDF in this direction, okay, we get the marginal at Versailles, which is this guy. If we integrate the joint PDF in this direction, we get the marginal temperature at Manhattan, which tells us, what the temperature is at Manhattan without, it doesn't matter what's going on in Versailles. Would you actually do this? Would you estimate the joint PDF from data and then integrate to get the individual PDFs? No, you would not, right? Because as I said a moment ago, you can also think of these guys as the PDFs of just the temperature in Manhattan. So you could forget about the part of the data point that refers to Versailles, just take all of the temperatures in Manhattan and do 1D kernel density estimation to find that density directly. All right, so what if we know the values of some variables and we want to update our uncertainty about the values of other variables? So in this case, maybe I'm standing here and I see that the otter is at that position of the lake. How does my uncertainty about A change? So if you want, you can imagine that my uncertainty about A is captured by this triangle marginal PDF. How should I update it? Well, the way I should update it is by taking the joint PDF, fixing the value that I'm conditioning on. Okay, so now this is a function of B, only of B. A is a parameter that tells me which of these conditional PDFs I should use to update. And we have this term that we're dividing by, which ensures that this is going to be a valid PDF that will integrate to 1. Okay, the same thing, it gets a little bit complicated, but let me walk you through. So imagine that you want the conditional PDF of one of the entries of a d-dimensional vector conditioned on the rest, okay? We're conditioning that the rest have these values. I'm gonna try to be consistent with the colors that I used before. Okay, so we fix all of those values. This is fixed now. And now we have a function that only depends on B. All right, only depends on B, the rest is fixed, but we need to normalize this so it's a valid PDF, and the way we normalize this is by integrating. And realize, what do we integrate by? This makes a lot of sense. This guy is just the integral of this guy with respect to every entry except B, so that this indeed integrates to 1. What is that equal to? It's the marginal of the rest of the entries. And no, I said that the other way around. No, okay, sorry. Forget what I just said. It's the opposite. It's what if we integrate? That's kind of funny. I'm not going to stop the video. You're gonna bear with me and forgive me for that. So I said it the other way. Let me say it again. What happens if we integrate this guy with respect to B? Of course, you integrate it with respect to B, right? Because then if you divide by that integral, then this whole thing is going to integrate to 1. So what happens if you integrate that guy with respect to B? You get the marginal with respect to the rest. Boom, that's exactly that. So now when you divide by that, everything is going to integrate to 1. So sorry about that. Okay, let's move on. What does this conditional PDF actually look like in the case of the lake? What are we doing? We're taking this slice of the joint PDF, which looks like that, and we're dividing by the value of the marginal there, which happens to be the integral of this guy. This is what I just explained. The conditional then looks like this, which is extremely different to the marginal. The marginal has this triangular form. So as you can see, conditional distributions can be dramatically different once we condition on other variables, different to the marginal. The definition of conditional PDF gives us the chain rule for continuous random variables, where the joint PDF is equal to the marginal times the conditional, and we can do it in any direction. Okay, any order works. Same thing for multiple random variables. Here, when I explain this, I think that I make it sound more complicated than it actually is. Here we have D entries, right? So the way we can decompose the joint PDF of the D entries using the chain rule is we start with the marginal of one of them, then the conditional of another given that one, then the conditional of a third one given the two first ones, and so on and so forth. Okay, and any order works, and you might need to choose the order wisely if you have conditional independence assumptions, which we often need because of the curse of dimensionality. Okay, so for temperature, let's take a look. Here we have, again, the joint of Versailles and Manhattan, but we're interested in finding out what happens if it's very cold in Manhattan. How is the temperature in Manhattan? Again, Kansas. How is the temperature in Kentucky? So this is the marginal of Manhattan. We're going to take this slice, divide by the value of the marginal there. That's going to give us the conditional distribution in Versailles, given that it's really cold in Manhattan. It's also very cold in Versailles. If it's 0 degrees in Manhattan, we see how the conditional PDF moves. It's a bit warmer in Versailles. 10 degrees in Manhattan, it's, like you can see actually that the temperatures in these two places are quite similar So here now the temperature is almost centered around 10 when it's 10 degrees in Manhattan. 20 degrees in Manhattan, the temperature is shifting. See that it's also becoming more concentrated, which is kind of interesting, to the point where, like, when it's 30 degrees in Manhattan, you're very sure that it's going to be hot in Versailles, and the spread of the distribution is much less. So there's less uncertainty about the temperature in Versailles when it's very hot in Manhattan than when it's colder, interestingly, which you can kind of see, right, from the, all of this you can see from the shape of the joint PDF. The conditional PDF just makes it extremely clear. What if we do this for movie length and the amount of money that the movie made in the box office? So this is the scatter plot of all the data points. This is the corresponding joint PDF. And this is the marginal PDF of the money that the movie makes. So most movies make very little money. Some of them make quite a bit. Now we're going to condition on movie duration. Okay, duration is here in the x-axis. When we do that, we see that actually the conditionals look very similar. This is for 90 minutes, 100 minutes. They look very similar among themselves and also very similar to the marginal PDF. 110 minutes, if I put them all together, they're very, very similar. There's maybe a slight difference. So it's possible that movies that are slightly longer make a bit more money within this range of durations, but they're almost the same. If these were exactly the same, then we would say that the two random variables are independent. Two random variables are independent if the conditional probability that one of them belongs to any set conditioned on the other one is just equal to the probability without conditioning. This is equivalent to the conditional CDF being equal to the marginal CDF, again equivalent completely to the conditional PDF being equal to the marginal PDF. Or we can express this in terms of the chain rule. In the chain rule, the joint PDF is going to be given by the product of the marginals because this guy is equal to the conditional. Same thing for multiple random variables. The joint PDF of the D entries of a D-dimensional random vector is going to factorize into the product of the marginal PDFs of each entry if the entries are independent. Now we're going to look at the temperature in Versailles and another place. So this is Versailles, Kentucky, and this is Corvallis, Oregon. Okay? This is the marginal in Versailles. This is the joint between Versailles and Corvallis, Oregon. So first we're going to check out whether these guys are approximately independent. This is what happens when it's 5 degrees in Oregon. This is the temperature in Versailles. 15 degrees in Oregon. Clearly not independent, right? Because you see this guy shifting. 25 degrees in Oregon. Again, this guy shifts, very different to the marginal. These two random variables are clearly not independent. But now let's see what happens if I condition on what's going on in Kansas, in particular in Manhattan, Kansas. How do we compute that conditional PDF? We're interested in the conditional PDF of Versailles and Corvallis given Manhattan. So what do? We fix the value of Manhattan, and then we have to normalize. So we normalize by the marginal with respect to Manhattan, and this gives us a function of two variables. This is a conditional PDF of these two variables given the third one. This is what the conditional PDF looks like. These are some points showing the temperatures in Versailles and Corvallis when in Manhattan the temperature is close to 15. So intuitively, this is what we're doing, right? We're taking those points and looking at their density. So this is kind of equivalent to what we're doing when we're computing the conditional density. Realize that this is very different to the shape that the overall density has. Very different. So now when we actually slice this thing at different parts and renormalize to get the conditional given Manhattan and Corvallis, so here what I'm showing you is the conditional just with Manhattan, and here is the conditional with Manhattan and Corvallis. It turns out that they're very similar. So this is Corvallis at 5 degrees, this Corvallis at 15 degrees. This guy stays the same, right? Because that's just the conditional with respect to Manhattan. This one should change because it's the conditional with respect to Corvallis, to Manhattan and Corvallis. It's this other slice. So here we're slicing here, now we're slicing there. You see there's not that much difference. It seems that once we take into account Manhattan, the dependence between Corvallis and Versailles is much smaller. Let's do it again. Now we have, remember that the overall density looks something like that. Now we're just picking points for which Manhattan is close to 25 degrees. Equivalently, we compute this conditional joint PDF of Versailles and Corvallis when it's hot in Manhattan. Realize that it's quite different to the previous one. The previous one was something like that. But it has this similar shape that is almost circular. And let's see what happens because of that. Now, again, when we slice the conditional, we again see that the conditional PDF given both Manhattan and Corvallis is actually very similar to the conditional PDF just given Manhattan. Okay, very, very similar. When this happens exactly, before that, let me explain that this makes a lot of sense because, you know, the joint between this guy and this guy, the dependence between this guy and this guy, once we know what's going on here, is obviously much smaller. If it's very hot here, you don't care what's going on here. Okay, or if it's extremely cold here, you care much less about what is going on in Oregon. It's not going to provide you much information if you're interested in what's going on in Kentucky. So that's the logic. When this is taken to the extreme and this guy and this guy are independent, given that we know what's going on in Kansas, then we say that the two random variables are conditionally independent. The definition mathematically is very similar to the one for independence. We say that the conditional joint PDF factorizes into the conditionals just given that variable. So here we're conditioning on C. Here we should condition on C and A, but if they're conditionally independent, we don't need to. It's just going to be equal to, so the joint is just going to be equal to the two conditionals just conditioned on C. Same thing when we have random vectors. If the entries of a random vector are conditionally independent given another random vector, then that means that the joint is going to factorize into the conditionals just given that guy. Okay? So it's the same idea, except that we're conditioning on one or several other random variables. The same idea as independence. All right, what if we want to simulate random variables at the same time? So for example, what if I want to simulate points in this triangular lake? Remember that we know how to simulate individual random variables by applying inverse transform sampling. So what you could do is you could say, okay, I know the marginal distribution of the vertical coordinate, I know the marginal distribution of the horizontal coordinate. Let's just generate points according to those distributions, basically taking uniform samples and applying inverse transform sampling. And, they should give me the right distribution, right? Well, these are the uniform samples. These are 2D uniform samples. Each of these guys corresponds to two uniform samples that are going to be mapped to A and B according to what I just said. If we do that, it just does not work. Why? Because we're simulating the random variables separately, as if they were independent, and they're not independent. We're not capturing their dependence. So what can we do to capture dependence? We need to first generate one of the samples and then generate the other sample conditioned on that value. Okay, we need to sample from the conditional distribution of the other one given that guy. If we do that, then it works out and we actually get samples from the triangle. This is explained in more detail in the video on simulating joint distributions of random variables. Okay, so we've reached our final topic. Remember, because of the curse of dimensionality, when we go to higher dimensions, we cannot do things like multidimensional kernel density estimation. We either have to enforce independence or conditional independence constraints in order to be able to estimate the joint PDF tractably, or alternatively, we can use a parametric model. And the most popular parametric model is the Gaussian parametric model. So the idea here is that we want to use the Gaussian distribution to model random vectors. The motivation is the curse of dimensionality, as I just said. Let's, do something. Let's start with a first very simple idea, which is we know how to model separately random variables as Gaussian random variables. We just estimate their mean parameter understand that deviation parameter, and we can do that for each entry in a random vector, right? We can just do that so that we're going to basically have a Gaussian model in each entry. The joint PDF that we get from that is just the product of the marginal PDFs. That looks like that. Okay, so here, this is the marginal of a Gaussian, and because we have a product of any exponentials, we can just sum the exponents. If we do that, we get contour lines of our density that look like this. Okay, they're going to look like circles in 2D or ellipses that have axes that are aligned with the coordinate axis. We can see that this is the case by setting the density equal to a constant. When is the density equal to a constant? When the exponent is equal to a constant. This formula for the exponent is the formula of an ellipse which is aligned with the coordinate axis. In the dimensions, it would be an ellipsoid. So that's not great, right? Because it doesn't allow us to even model this cloud of points, even though the cloud of points is clearly ellipsoidal. So it would be great if we could have essentially the same model, but we could rotate the ellipse. And that's exactly what Gaussian random vectors allow you to do. That's it. Okay, there's nothing more to Gaussian random vectors than that. We want to have ellipsoidal contour lines of the density that decay exponentially, and we want that those ellipsoidal lines to be rotated with respect to the coordinate axis so that we can essentially capture dependence, right? So here the problem with this model here is that it's not capturing dependence. It doesn't understand that. It doesn't capture the fact that taller people have longer feet. Okay, so we want to be able to rotate this ellipse. What do? We include axes of the ellipsoid into our model. So now we modify these contour lines by adding these axes that essentially allow you to rotate the ellipse. You can write this in matrix form. Again, we explain this in more detail in the video on Gaussian random vectors. And if you do that, essentially you get a parametric model that is parameterized by a single matrix parameter that encodes how these axes are rotated and also what spread you have along each of those axes, and that's called the covariance matrix parameter. Once we do that, we get this new formula for the joint PDF of the Gaussian random vector, which enables us to have ellipsoidal contour lines that are rotated, and we get much better fit to our data in this example. This is the definition of the Gaussian random vector. We have two different parameters, the mean, which tells us where these contour lines, where this cloud needs to be centered, and the covariance matrix, which tells us how these contour lines, how these contour lines should be rotated with respect to the to the coordinate axis and how spread out you are in each of those directions. It turns out that once you define the joint PDF like that, the marginals and conditional distributions are all going to be Gaussian, which is very nice. We proved this in this separate video. I don't have time to go over that in this one. I don't want to make it too long. And when we want to estimate the parameters from data, we use maximum likelihood. So essentially, we write down the log likelihood of the data that we have. Now the data have to be d-dimensional points, because remember, we're modeling the joint distribution of d quantities. And it turns out that the mean parameter for the Gaussian is just going to be the average of the d-dimensional points. You average each of the entries. And the covariance matrix parameter happens to be equal to the sample covariance matrix, which, as we will see later on, essentially captures the variance in every possible direction of space. And that's it. What have we learned? We have learned the mathematical definition of multiple continuous random variables belonging to the same probability space, which allows us to jointly model multiple continuous quantities. We have learned about the joint probability density, which is really our user interface that we use to manipulate multiple continuous quantities together. We have learned about marginal distributions that enable us to isolate the individual behavior of continuous quantities within a model with many variables, and also conditional distributions, which allow us to update our uncertainty about individual variables, given that we know the value of other variables. And finally, we talked about this parametric model for multiple continuous variables, which is the Gaussian random vector parametric model. And that's all I got. Thank you very much.